Bob, thank you for that introduction. Can everybody hear me? All right. I like the stage. It almost feels like I'm giving a TED talk or something, you know. Yeah, I'm going to talk to you about Hurricane Ida. And I have a question up here. Is that a preview to the future? And of course, I can't really educate you much on what Ida did to this area. You all know that better, much better than I do. And but there's some peculiar things about Ida that I think are worth talking about. And I'm going to show you my outline here. It's old school. You got the nice outline there with the introduction, motivation and goals, data methods and results, and then the summary and conclusion. And I teach seminar back at University in Missouri, so I guess I got to lead by example on that. So, but good old-fashioned outline. All right, so is it? Am I pointing it? I must be. Oh, I must have to point it in that direction. Okay, so again, Ida was a very damaging and a very destructive tropical cyclone. All right, it reached high-end wind speeds of 150 miles an hour and hit a minimum pressure of 929 millibars, which is fairly low. It put it into the much stronger category of Atlantic storms that we've seen historically. All right. And the remnants of Ida also caused trouble in the Northeast United States, some of the same areas that were affected by Hurricane Sandy. And I'll tie Ida into Sandy later on. All right. I don't know if you can see this. Well, I think you can, because I'm looking at that screen, which is tiny. This one is a nice big one, and this shows you all the storms that occurred during 2021 and out in the Atlantic. All right, we had 21 storms in 2021, so it was a very active year for the Atlantic Ocean basin. And Ida's number 9 here. She began in the Caribbean and made her way across Cuba, where she did some damage as well. And the forward motion of Ida slowed as it reached the Louisiana coast. And one of the peculiarities about this is not only did it slow, but it kept some of its strength as it moved inland. Then it moved out over the Appalachians area and reorganized over the Northeast after ingesting some more moisture. And here's the single trajectory of Ida. And this single trajectory shows you basically her path as well. All right, again, it was a very destructive storm. All right, $75 billion storm. All right, we've heard lately that there's been an increase in these billion-dollar disasters. All right, and of course, that's because of inflation, but it's even pretty destructive, even if you adjust previous years and previous storms for inflation. So it caused a lot of heartache. And of course, it caused a lot of casualties as well. All right, 87 people were killed by the storm. And of course, that's never what you want to see. All right. Ida did, again, as I said, it moved very slowly as it came inland. And we can remember that Hurricane Harvey in 2017 stalled near Houston and dumped as much as 63 inches of rain in that area. And I kind of think we have something here. I think we have something to explain this, and when I get to that message, we'll show you the meteorology of that. All right. Again, Ida began in the Caribbean, as I said before, moved up through the Cuban area, hit Louisiana, and then into the mid-Atlantic. And over the mid-Atlantic, I want to show you some of the rainfalls that happened over the mid-Atlantic, because that's pretty interesting. all right? It gave 5 inches of rain over a very large area of Pennsylvania, Delaware, New Jersey, and Connecticut. So I've got some maps to show you that. All right. There were also tornadoes as this thing moved inland. All right. Typically, when you get storms like that, they will drop tornadoes, but as it approached the East Coast, the moisture that it brought in from the Atlantic and its transition to more of an extratropical cyclone dropped a few more tornadoes that were pretty destructive in the Northeast. And on this, on the left-hand diagram, you can see general areas of 5 inches of rain or more in the orange and red. It's hard to see. The orange and red you can make out as different from the green. So again, you can see over a very large swath. You saw some 5 and 10 inch rains in the Northeast. All right. And over here, this is an interesting map because it shows you the largest amount of rain in every state from tropical systems. And you can see that Ida did not drop the most precipitation in Louisiana, and it didn't drop the most in the Atlantic area as well. I mean, the amounts that were received were tremendous, but they didn't break records, all right? But this is kind of an interesting map because how many of you would think of tropical systems dropping moisture in Montana or North Dakota, right? Not many of us, but you can still see that even in the northern United States, tropical systems will bring moisture that far inland. Okay, so there is a lot of concern. We've heard it lately with Hurricane Ida. We heard it last year with hurricanes that struck Florida. All right, there was Hurricane Michael that hit Florida a couple years ago and grew explosively. All right, there was that hurricane, I think it was Damien or Darren that hit the East Coast a few years ago that also moved very slow. There's a lot of concern that we're getting more stronger hurricanes as climate changes because of a more vigorous water cycle. So there is some concern about the human contribution to these storms, all right? And again, research can't really answer that. Can't really answer that for one storm, but we can answer some of the questions in a more climatological sense, right, over a long period of time. And we can also look at some of the reasons why Ida stalled, all right, whether people are contributing to the changes that are happening or not. We can still look at the meteorology involved, all right. So that's what we're going to do here. That's what we're going to do here. And again, we need to be prepared for changes in the frequency of storms hitting the United States, simply because from 2005 to about 2018, 2019, we were just plumb lucky here in the United States that there weren't very many landfalling hurricanes. All right, it was a fairly long period of time not to have strong landfalling hurricanes, even though those 2 decades were fairly active out in the Atlantic. All right, so some of my data sources, all right, are sources that you would expect. The National Hurricane Center, all right, their website gives an archive of all these storms and a summary of the meteorology that comes with them, including damage estimates and things like that. The National Center for Environmental Prediction Reanalyses, these are some of the maps I'm using. I use the COCORAS data, Community collaboration on rain, hail, and snow network. This is a network of citizen gauges. All right, the head of that is out at Colorado State. This Colorado State climatologist developed this program back in 1998, where citizens could report their rainfall records to a central location, and it helps to give us more information. The Weather Prediction Center, University of Wyoming weather, I used to get some maps. And then the University of Missouri, my own archive of what we'll call blocking events, and I'll talk about that later on. All right, so this look at the future is going to be mainly a synoptic and dynamic analysis. All right, when we look at the path of Ida. All right, so that's going to be mainly a qualitative look right now, because I'm not too deep into the research yet. I really need to get a proposal out there about this, but I also could use a graduate student or two to help me with the project. All right, and we'll look at the climatological aspect through some numbers that we can easily gather. And then I'll talk about the brown ocean effect and what role that may have played. All right, so some very important questions when it comes to storms like this, climate and climate change. Can we expect more of these? What do the trends say? All right, what are they telling us? And what does science say? What does science say? And there's a good repository of research articles that discusses this, that's contained in the IPCC volumes. So we'll actually go to their research. All right, a study that we did about the decadal trends in storm activity. All right, we published one in 2020 that tried to normalize global activity and look at the most recent period. All right. In the Atlantic, you have tropical records going back to the 1940s and even before. In the East Pacific, you only have them since 1970. In the Southern Hemisphere, you only have reliable records since 1980. And since that was the first time that we had good global records, our study took off from that period. And what we showed is that globally, tropical cyclone activity is on the rise, but the number of hurricanes is slightly down. All right. And we see a trend in the Atlantic where tropical cyclone activity is on the rise, and Atlantic hurricane activity is also on the rise. Now, a couple things about these trends before we move on. This trend here is not statistically significant, and neither was this one. All right, so we do see this rise, but it's not significant, and the fall is not significant globally. In the Atlantic, however, these rises are statistically significant at P equals 0.01 if you want to write it that way. All right, so it's a strong indicator that these rises are significant in the Atlantic. All right, and in the Atlantic, all right, the number of tropical events is certainly on the rise. The number of hurricanes only, and the major hurricanes. So the Atlantic hits the trifecta, all storms, minor hurricanes, and major hurricanes. All right, but globally, the major hurricanes are increasing, and that's statistically significant. And that's driven by the Atlantic Basin, the Indian Ocean Basin, and the Southern Hemisphere. Those three basins have shown some fairly strong increases in powerful storms. Now, before we get too excited about that and say, well, this is a this is something that we've got to be careful of. Well, we do. We certainly have to be careful of this. But remember that it's only been since recently that we've put up some satellites that can analyze things more clearly than ever. And so some of this intensity change may be driven by technology. Some of it may be driven by better sensing near the surface. But remember too that wind speeds, all right, judging wind speeds, and wind speeds have a accuracy of about, or an error bar of about 5%. So sometimes wind values can be a little bit suspect. And of course, globally, again, we see this increase in major hurricanes. Now, could it represent a real trend? It certainly could too. It may be a combination of things. We can't rule that out. All right, and in other regions, like the East Pacific, the West Pacific, we see that the trend for the number of hurricanes is actually down. The West Pacific especially. The West Pacific is usually the noisiest basin for tropical activity, but in the past few years, it's been fairly quiet. All right. All right, in the Atlantic, we see that the storm season is starting about 2 weeks earlier than it did. We're seeing more May storms. We're seeing some even happen in April. All right, nominally, the Atlantic season begins on the 1st of June. All right, which is still a little ways away, but again, we're starting to see some of these come earlier. All right. And there's definitely a tie-in between the strength or the occurrence of hurricanes and the phase of El Nino. All right. La Nina years tend to see more hurricanes and tropical systems. And we've had 3 straight years of La Nina, which I hope we're going to break here soon. All right. You can see that in 2020, we had 31 events, 2021 and 22. 21 events, and I think we ended up with close to 20 for this past year. All right. All right, again, what does the future hold for us? All right. At least the trends seem to be pointing in some basins to an upward direction. All right. So what does the literature say for the future? All right. They conclude in the IPCC that the total or overall frequency of tropical cyclone activity may not change appreciably, but there's a caveat to that. All right, the IPCC says it is likely that there's been an increase in the proportion of storms that are more intense. And like I said, we're kind of seeing that. So the IPCC is confirming what my study showed, or actually more appropriately, I'm confirming what the IPCC showed, being one person out there. All right, so there is little or no trend in the frequency of USA landfalls. All right, we haven't seen that, thank goodness. And we did get that statistical break that I talked about where we just got plain lucky. All right. When scientists run the models and count up the number of storms that we could see in the future, all right, there's very low confidence in long-term trends. And there's also very low confidence in observed long-term trends. All right, so whether it's modeled or observed, we don't have much confidence in the long-term trends. But again, there's high confidence among modelers that we may see more of a trend towards stronger storms. But then there's a caveat to that as well. And that is there's really no consensus among folks who study tropical systems, all right, on the relative magnitude of human versus natural influence on the trends that I just showed you. All right, so, you know, that's the scientists themselves speaking on that. So the record is kind of mixed, but what does that mean? All right, I think it means, again, the higher confidence in the number of stronger storms and all right, and the fact that we just got through a period that was quieter means that we need to be extra vigilant along the Gulf Coast and along the Atlantic coast. All right, at some point, statistics will catch up with us. All right, let's talk about the meteorology of why the storm may have stalled. All right, why Ida may have slowed down. All right, and to look at the things that influence hurricanes and their movement, I'm going to invoke Hurricane Florence. Hurricane Florence occurred, all right, between the 30th of August and September 18th. And we studied this one because one of our master's students ran some WRF simulations of Florence as she approached the Carolina coast and then stalled there. So we'll look at some of these things. Now, when folks look to predict what steers or what levels steer hurricanes because of their deep convective structure, we look in basically most of the free atmosphere, the 850 level to the 300 hectopascal level. All right, that's about 1.5 kilometers up to about 10 kilometers up. All right, and of course, I'll probably show you, if I'm not mistaken, probably show you the 500 millibar map since that's about halfway up. Well, here's the track of Florence. Florence began near the coast of Africa. It started moving and deepening, and then it began to recurve as storms usually do. Then it ran into high pressure in the mid-Atlantic, and it kind of bounced off of that and moved toward the west, and then it began to recurve again toward the coast of the US, came inland, slowed a bit, and then got carried out. All right, and this storm again caused a lot of flooding. Well, why did Florence do that? Why did she take that weird turn? All right, well, let's take a look at that. All right, we published in Belkacem et al. 2020 the effect of high pressure that happened in the northern hemisphere, all right, to deflect the storm. Now, what happened was in the late part of August and in early September, the northern hemisphere flow as a whole, all right, was fairly wavy. All right. And then around the 5th through the 7th of December, the northern hemisphere flow changed its course and became more zonal. All right. So let's show you what we mean by that. All right. Here's, again, the 500 millibar map. That's about halfway up the atmosphere. All right. Hurricane Florence was right in this area. All right, and we see kind of a flattened ridge pattern over the Atlantic, and a ridge pattern is going to have winds that circulate clockwise around that. And so those winds in the central part of the Atlantic are basically going to block the path of Florence and deflect it back to the west with that flow that's doing this. And I think I've got a map that shows that quite nicely. This is the vector winds. All right. Now, the vectors on the map are in black color, so it's hard to see against the blue background. So I put this white arrow here so that it'll stand out against the blue. All right. And the vectors in this area are doing exactly what I said it was doing over here. So Florence was blocked and deflected to the west. And again, that's what tropical forecasters look for when they look at the path of these storms. Well, in Ida's case, what happened is we think the jet stream was too far north to have an influence in picking up Ida. What usually happens when storms hit the coast, they hit the coast in September, October, and even August. The jet stream will pick these things up and carry them off very rapidly. In Ida's case, the jet stream was not close enough to do that. And that's what I want to show you. And why was that? Well, if you attended my talk last night, we talked about blocking stationary anticyclones in the mid-latitude jet. And what we had at that time over Europe was some unusual blocking. What was unusual about it was its strength for the time of year. It was a fairly strong anticyclone event. All right. And it existed over Europe from about the 23rd of August to the 5th of September of 2021, or about the time Ida lived. All right. And we can see what this blocking event looks like. It's basically, if you're not a meteorologist, you read this map like a topographic map. It's basically a mountain of air in the atmosphere. All right, over Britain. And you might say, well, that's over Britain. How's that going to affect us here at the Louisiana coast? All right, well, Ida moves ashore. This strong blocking is preventing the regular progression of jet stream waves over North America. That's why they have the name blocking. They prevent the progression of shorter waves. All right. And those waves were of too small of amplitude to capture Ida. That's our thought. And this is what happened. This is the 31st of August as Ida's coming ashore. Actually, she's already ashore. You got that strong blocking over Britain, and you've got this train of short waves that's just backed up here like a traffic jam because the darn blocking event's in the way. And again, you can see their amplitude is fairly small, and they're located about 2,000 kilometers away from Ida. Well, why is that significant? All right, as Ida moved northward, and I'll talk about why that's significant because it's really an old idea, but I'm going to put a new spin on it. All right. All right, strong blocking event still prevented Ida from going, but because those waves were backed up, what happened is these waves began to amplify and they finally picked Ida up. They finally picked Ida up on the 1st of September. Look at how much these waves have amplified in a rough 36 to 48 hour period. Now Ida's picked up and she's going to go out to sea like they normally do. All right. All right, so you say, well, what does this have to do, again, what is this idea that Ida was too far away originally? Well, some old meteorologists, H.L. Quo and folks like that, and Edie, I don't know if any of you have heard of those names, they postulated how far waves had to be away from each other to interact. And it turns out that they have to be quite a ways, or they have to be quite a bit closer than 2,000 kilometers. Now, they didn't give us any numbers at the time, but a study by Castman et al. Looked at how close jet streaks had to be to interact with each other over the United States. and they determined that roughly 1,100 to 1,500 kilometers is key. 11 to 1,500 kilometers is key. And that distance was determined using something called the Rossby radius of deformation. Rossby radius of deformation is just the relationship between buoyant forces and inertial forces, but it also serves as a cutoff between what we think of as synoptic scale phenomenon, purely geostrophic two-dimensional phenomenon, and mesoscale phenomenon. So as long as these things are closer than 1,100 to 1,500 kilometers, they'll interact. And that's what we saw with Ida. At first, the jet stream was just too far away to pick it up. That's why it stalled. We saw a similar thing with Harvey, saw a similar thing with Florence. So now, again, I need a grad student to help me quantify all this. All right, so Castman et al. Was the key, all right? Again, looking at waves that are within that Rossby radius of deformation. The idea, again, is not something new, but the estimate of the size is new. So Ida moves ashore, the storm slowed down, and it interacted with land, but then it lost intensity a little more slowly than we normally think of. All right, so we'll talk about that as well. But at first, it was just too far away from the jet stream to get picked up. All right, by September 1 to 2, again, the Ida moved out to sea, and that's where it picked up a lot of moisture from the southeast Atlantic and dropped it on the northeast. All right, so here's the 850 millibar map showing, oh my goodness, the color scheme is not very good, but again, here's Ida on the 2nd of September drawing moisture out of the Atlantic and dumping it on the East Coast. All right. Oh, this is a better picture. All right, here's the surface map. Here's Ida on the, let's see, what date is that? This date's not showing. I think that's September 2nd or September 1st, and then this is September 2nd. So Ida did cause a lot of problems. Now, why didn't Ida lose its intensity very quickly? Well, there's something called the brown ocean effect. All right, and what's the brown ocean effect? All right, it's something that Professor Marshall Shepard at University of Georgia postulated. He said that normally storms over land will decay, but if those land surfaces are sufficiently wet, they might act more like ocean in supplying the storm with the energy that it needs. Maybe not as much as the oceans, but enough energy to keep that storm going. And in fact, Dr. Shepard's study looked at a case where a tropical event developed over Oklahoma, right? Because the ground was just so wet that it temporarily, after it moved ashore and weakened, it temporarily gained strength from the wet ground. So this can happen. This can happen. And was the conditions ripe for that in 2021? Well, let's try and look at that. Let's look at precipitation. Oh my goodness. Everybody, if you were here in 2021, you remember how wet that was. All right, you can see that the precipitation anomalies are rather high here in the southern Gulf region. And the evaporation, well, not much evaporation during the spring season. So you had plenty of moisture available. All right. So maybe Louisiana was experiencing the brown ocean effect when Ida came ashore. All right. All right, so let's summarize this. Let's talk about the important effects or the important details that came from this look at Ida. All right, Ida was a fairly large storm. The peculiarities of Ida was how slowly it moved inland and how slowly it lost strength. It caused a lot of damage, all right, in both the Louisiana area and the Northeast. All right, there is concern that we may see more storms like this. Again, Harvey, Ida, all right, a couple of these storms have moved slow enough that people have been concerned that we might see more of this. All right. When we look at the trends, we do see there has been an increase in stronger storms. All right. But past trends, much before the middle of the 20th century, and future trends are fairly unclear. The only thing that the IPCC is confident about is the increase in strength and increase in proportion of stronger cyclones. We did see it move slowly inland, all right? And because the jet stream was just too far away to pick it up. All right, so that's something I want to look at. Also, as Bob said in the introduction, a lot of my studies are done on mid-latitude events like blocking. And so I want to see what the role of blocking may have been in causing the jet stream to be too far away. All right. So what is the effect of the dynamics? And then it's possible that the brown ocean effect may have been problematic in the decay of Ida, right? That it didn't decay as quickly because of this effect. Right? So we need more studies. We need more studies. Isn't that the message of every scientific seminar? We need more studies. All right. And I think that is a good conclusion, that we do need to study these things further in order to figure out what's going to happen in the future. So, any comments, any questions? Yes, sir.
Does the CC or any other times that suggest that the Gulf Coast region will receive like how high precipitation anomalies in coming years, particularly cascading?
Precipitation anomalies. Yeah. I'm going to tell you that I didn't look at that, so I'm not sure. But I will, but that's something that we do, that would be worth checking out. So yeah, you're absolutely right. Because if we get more precip, that would be a bigger effect. I saw your hand first, and then we'll go here and there. Yeah, blocking occurs roughly 30 to 40 times a year. The only thing that was unusual about that blocking event was just the strength of it for the time of year. And that was the one thing that was unusual. But you don't hear about blocking often, because most of the time they occur over the oceans or out over Asia. And so American meteorologists very rarely talk about it. And in fact, North America is where they occur the least. So, yes.
Those
Well, that's also a good question because a lot of times they reach their maximum intensity out over the ocean. And these trends toward an increase in intensity are not huge. You know, as of yet, they're not doing something like this. And fortunately for us, as they do approach land, they tend to weaken a little bit. But this one was a little unusual because of that brown ocean effect. So yeah, there's a lot of questions to answer about the intensity effect there. And then your question.
Question is, maybe in lieu of the balloon level that's going on now, how do you collect that much data showing contours over the whole globe? Are those modeling estimates or their sensors that are actually stopping that data?
Excellent question. Yeah, a lot of that 500 millibar data for the NCEP reanalysis is based on balloon flights. And then what they do is they collect that information along with satellite information and ground-based information, and nowadays even airplane observations. They gather that together, they QC it, and then they contour, or they, you know, over the oceans, they need to interpolate it to give you this grid. And so over the oceans, obviously there would be more questions about the precision and accuracy of that data, but over land, it's pretty good. Some wavelengths in the air that exchange that we're looking at it from the satellite. And how do you know out something physical being up there later? Wind speed is X or the flow is X. There's nothing special that I'm aware of. No, you're right. Anytime you do these kind of interpolations or things like that, the wave number may be, quote, aliased to a different wave size or wave height. So there are issues like that. I think there's a lot of confidence, though, that the measurements we're coming up with and the interpolations that we're making are pretty good. And so I think we're just at a point where we're confident in the technology, but you're right. Without an absolute measurement, it's impossible to say for sure. And of course, that's part of the problems for forecasting today is, are we representing the initial state correctly? And so that's, of course, what leads to forecast degrading 5, 7, and 10 days out. So it's a good question. It's a good question. Yep. Natural wetlands leading to the brown ocean, or the removal of them. I'm not aware of any studies myself, and I'm not, so I won't say for sure if there are or not, because I just don't know. We're not deep enough into the research yet. So, Bob.
Step back just a little bit and talk a little bit about polar amplification and how it relates to the slowing down of systems like Harvey and many other hurricanes in recent years. And then, if you will, just briefly, as you probably know, there's still a debate, I think, going on about the response of those waves to that polar amplification if it continues, and whether the waves that you're seeing with smaller wavelengths and lesser amplitudes is what you would expect to continue.
Yeah. There. Oh, you're No, you're absolutely right. The large scale folks, Vavris and Francis against the folks in Britain, Barnes and them. Some folks have theorized that with a warmer world, as you decrease that equator to pole temperature gradient, what you do is you get a wavier jet stream. And that wavier jet stream also will be more stationary. All right. That's a possible outcome. Another possible outcome that the folks in Britain adhere to is that the jet stream will be similar today or even more zonal, but will vary its wind speeds in a greater way. All right, so there's two distinctly opposite looks at how this may come out. And there's a formula. I'm not going to get into the exact formula for the Rossby wave speed, but there's two issues there. All right, there's the strength of the jet stream and the wave number, and they interact very non-linearly. So it's very tough. It's very tough to see who's right using that equation, but both camps' results are supported by that equation. So it's not a easy thing to untangle. So, well, I'll tell you that personally, when I look at future scenarios and wave dynamics and things like that, I think the folks in Britain are more correct, but that's just my opinion right now. So we'll see how that changes in the future. So. Yes. Hurricane Isaac. Oh, is that one that, or Ivan, it might have been, that came up and circled back around and then came through again? I'd have to look at the maps to make a real good judgment on that, but my guess is that it got picked up as they normally do, all right, and moved toward the northeast, and then something out in the Atlantic forced it to go south, and then it came back and did its thing again. I'd have to look at the maps for that, but that would be my guess as to why it did that. Yeah.
I get the term the brown, the plant you called it.
Yeah.
Your example was in Oklahoma, I believe.
Yeah.
I've also heard, and maybe I don't know if I'm talking about, but sort of tropical characteristics of storms developing over the Great Lakes. So I'm curious, with climate change, is there a chance that more tropical storm-like events could happen in more terrestrial habitats, and they're not just going to be ocean phenomena?
Well, there are, the Mediterranean and the Black Sea also have these quasi-hybrid tropical, extratropical storms. And in fact, we published on one that hit the Black Sea region near Azov in Russia. And these kind of events there are fairly natural because the sea surface temperatures are just enough to support quasi-tropical characteristics. I would say that if the Great Lakes were to become that warm, it's possible, but it would be rare. It would be rare. So. Actually, in Missouri, we can use the example of the drought of 2012 as a good example of that. 2012 was severe, and at that time there was a storm, I think it was named Isaac or something like that, in the Gulf of Mexico, and every Missourian was saying, please come, please. And it ended up coming, and it dumped only about 1.5 to 2 inches, which was enough to relieve the drought somewhat, but it wasn't enough on its own. So in the case of 2012, people were praying to God that it would come up and hit Missouri. And of course, that's bad for the coast, because in order to get to Missouri, it's going to have to come through those areas. But these things can help to alleviate drought conditions in places that are inland. So, and 2022 is also a very strong drought year, and we've actually published some on that. So, and that we've linked to teleconnections in the jet stream. So, any others? Yes.
Does that indicate that there could be more people there?
Possibly. I think what you're talking about more is if you've got a stronger water cycle, then you'll see stronger interannual variability in the precipitation in places like Louisiana, Missouri, Arkansas. Missouri, when I go out and talk to people about Missouri's weather, I say we're basically a feast or famine state. You know, it's very rarely normal. We're either dry or wet. And if you see this kind of variability increase because of a more vigorous water cycle, then yeah, you'll see a more strong precipitation interannual variability. And I think we have seen that in the last 2 decades in Missouri, where you whipsaw from a dry to a wet year. So, yep.
This question is really not related to your talk, but since we survey the global trends of hurricane activity, I just like to pick the blame. I think 2004, there was a first tropical cyclone that occurred in South America, affecting the east coast of Brazil.
Oh, yes. Catarina. Yeah.
Category 2.
Yeah.
And so at that time, a lot of meteorologists were puzzled as to whether this is really a game changer, something that is that mark the beginning of a new trend of hurricane activity in the South Atlantic Ocean. But some people also regarded it as an anomaly. So I'd like to know your perspective on the question of whether you might begin to see more or more activity, hurricane activity in the South Atlantic.
Well, the case of the South Atlantic in that case, yeah, I think that was an anomalous storm, and we looked at that one. Actually, I had a master's student look at that one, and what was peculiar about that storm was that it benefited from what we normally think of as mid-latitude forcing, but it kept its tropical character, and you probably do see these things from time to time in that area, but we just haven't had satellites covering that area for more than 40 years, right? So the fact that we haven't seen one there since like that kind of tells me that it was anomalous, but the better satellite coverage that we have tells me that the occurrence of extra or hybrid tropical, extratropical cyclones in that area is far more numerous than we originally thought. There's at least a handful of storms down there every year. Hybrids or maybe even true tropical storms. So we're finding a lot more of these with better coverage.
Do you think that that's at least partly a result of better surveying and observation?
Yeah, that's kind of like tornadoes. I mean, we really can't say much about trends in tornadoes as related to pattern changes, at least really not yet, because in the last 100 years, we have radars now that better count these things. Everybody and their uncle has a camera now and takes pictures of that, takes a selfie with a tornado and look at the tornado. Yeah, so and there's some people who think that we still miss quite a few of those. Because if a tornado blows out in the middle of Nebraska and nobody sees it, all right, it still occurs, but it never gets counted. So and tornadoes, of course, have a strong population bias as to where they occur. So I think it's somewhat akin to that phenomenon. Yep. Well, thank you. Thank you. Yes, I don't want to be the one standing between you and lunch, so